Welcome everyone to today's webinar, Urban Positioning 3D Mapping Aided GNSS using Dual Frequency Pseudorange Measurements from Smartphones, which was published in the winter 2021 issue of Navigation, Journal of the Institute of Navigation. You can download this article and many more on the Navigation Open Access website found at navi.ion.org. The website has tools that allow you to read, download, cite, and share valuable research content such as this paper. Today's webinar is being presented by two of the paper's authors, Ivan Ng and Dr. Lita Xu from the Hong Kong Polytechnic University. Mr. Ivan Ng received a Bachelor of Engineering in Air Transport Engineering and a Master of Science in Mechanical Engineering from the Hong Kong Polytechnic University in 2018 and 2021, respectively. He's currently a PhD student in the Department of Aeronautical and Aviation Engineering at the Hong Kong Polytechnic University. Dr. Lita Xu received a BS and PhD degree in Aeronautics and Astronautics from National Cheng Kung University in Taiwan in 2007 and 2013, respectively. He's currently an assistant professor in the Interdisciplinary Division of Aeronautical and Aviation Engineering at Hong Kong Polytechnic University. We greatly appreciate the time and work that Ivan and Lita have put into today's webinar. Following the presentation, we'll take questions. You can ask a question by clicking on the Q&A box in your viewer. So thank you for being here. And now we'll turn it over to our presenters.
And thank you, Rick, and welcome to this webinar. And that's my great honor to be today's speakers. And my name is Hoi Fung Ng, or you may call me Ivan. And we also have Dr. Lita Xu here. And we come from the Department of Aeronautical and Aviation Engineering, the Hong Kong Polytechnic University. Our paper titled Urban Positioning 3D Mapping Aided GNSS using Dual Frequency Pseudorange Measurements from the Smartphone. As we know, the GNSS positioning can provide an absolute position, but the performance is not satisfied, especially in the urban. And the positioning area can achieve for 100 meters or above in the urban area when using the weighted square method, which is only a pseudorange, which is using the pseudorange measurement only. And this large positioning area is come from the measurement area, which this GNSS satellite can be blocked or reflected over the buildings, which creates two phenomena. The first one is the NLOS reception, which the line of sight signal is blocked by the buildings, and only the reflected signal can be reached to the receiver. And the other phenomena is the multipath effects, which both the direct signal and the reflected signal can be received with the receiver simultaneously. And different research have been implemented that try to improve the urban positioning. And one of the great methods is using the 3D building model to help our GNSS positioning, which is a powerful resource that the digital twin methods try to digitalize our real world and using the 3D building model to represent our real world. And we can use this kind of resources to help our positioning. And we call this method is the 3D mapping aided 3DMA GNSS. But what can a 3D building model do? The first one is a satellite visibility prediction. For a given location, we can using the surrounded building features to extract the building boundaries. And we call this sky mask. The sky mask is the highest elevation angle at the surrounding azimuth angle on each surrounding azimuth angle. After we put this satellite sky pod to it, for the satellite that falls inside the gray area, we can assume it is a NLOS satellite. And the other powerful function of the 3D model can do is the transmission path propagation. For a given location and the position of the satellites, we can identify the blockage of the signal. On the other hand, we can evaluate the reflected signal and we can correct this reflected delay for these measurements. But however, it is actually a chicken and egg problem that we have to know our exact location to predict or to estimate the area of the measurements. Therefore, the 3DMA GNSS is usually a particle filter-based approach that we try to distributing the position hypothesis candidates and try to evaluate the likelihood score. And in theory, if the candidate is near the truth location of the receiver, it will have a higher similarity between the simulated and the received measurements. And this concept have developed different popular methods of the 3DMA GNSS, which the first one is shadow matching. Shadow matching is using the satellite visibility as the positioning basis, and the other one is the ray tracing GNSS, which is a ranging-based 3DMA GNSS. And we believe that different commercial applications have implemented the 3DMA GNSS in their product, such as the Google and the Uber. And let me just quickly introduce different kinds of 3DMA GNSS. The first one is the shadow matching. Shadow matching is try to compare the find the position of the highest similarity of the satellite visibility. And after receiving the satellite, we can try to evaluate the visibility prediction at different candidates. And we are going to using two locations here, which is the location T and the location 1. And if we try to compare the visibility similarity, we can see that the location T will have a higher similarity on the satellite visibility. Therefore, it is more possibly as the receiver location. And because of the building geometry distribution, the shadow matching usually perform well in the across street directions. But however, the strong NLOS reception may degrade the performance of shadow matching. Using back this example, if these 3 satellites become a strong NLOS reception, which means that it will be received by the receiver and become a green, the location 1 will possibly will wrongly identify as the truth location of the receiver. And the other 3DMA approach is the ranging-based 3DMA. Similarly, it is trying to find a location that have a high similarity between the predicted pseudorange and the measured pseudorange. And in here, if using this example, we can try to evaluate the similarity of the pseudorange and comparing at different candidates. And here, the location 1 will have a higher similarity. So it's possibly as the location for the receiver. And moreover, inside the pseudorange simulation, the ranging-based 3DMA will try to repair the reflection delay for the NLOS satellites. And it is quite important for the 3DMA GNSS, and it is powerful because for the for the conventional method, we will try to exclude the unhealthy measurements, which is this NLOS satellite. But inside the 3DMA GNSS, we try to keep using the NLOS measurement, and it can improve the satellite geometry, which is the dot value will be decreased, and we can get a better positioning accuracy. And because of the healthy measurement, which is the lost satellites, usually distribute and in the along street direction. Therefore, the ranging-based 3DMA usually perform well in the along street direction as well. And there is different approach to estimate the reflection delay. The first one is the geometrical-based method, which try to find the possible reflecting point and calculate the reflection delay. And the first method is the ray tracing GNSS, which try to testing all possible transmission path over all reflector. And here's a quick example. If we have a location of the receiver and the satellites, we'll first try to find the mirror point of the receiver and connecting the mirror point to the satellites, and the intersection on this reflection surface will be the reflecting point. And the other geometrical-based 3DMA GNSS is the SkyMask 3DMA, which is a computational reduced version of ray tracing GNSS. It tries to determine the reflecting point over the enhanced SkyMask. And the other one is a mathematical base, which try to using the distribution model to model the pseudorange difference. And it's called likelihood-based ranging GNSS. It is using the skew normal distribution to remap the measurement innovation. And in this study, we try to integrate different kinds of 3D GNSS, which the first one, shadow matching, which usually perform well in the across-street direction. And the second one is the ranging-based 3D GNSS, which usually perform well on the along-street direction. And in this study, we are going to use the SkyMass 3D and also the likelihood-based ranging 3D for the ranging-based 3D GNSS. And in their complementary nature, the integrated solution should be improved in the both along-street and the across-street direction. And we are going to integrate in the candidates domain, which try to take the square root of their product of the score as the integrated solution score at each candidate. And in the simulated pseudo-range parts, for the ranging-based 3D we are trying to find a location that have a higher similarity or the smallest pseudo-range difference on the measured pseudo-range and the simulated pseudo-range. And inside the simulated pseudo-range, it consists of the geometric range, the constant value, such as the speed of light, and also the model provided value, such as the satellite clock delay and also the ion-strike and the tropostrike delay. And for the NLOS classified satellites, the 3D GNSS will also provide a correction for the reflection delay. However, the receiver clock is a large uncertainty inside the pseudo-range simulation. Therefore, this study also tried to compare different clock modeling methods, and we're going to introduce in the later slides. The first receiver clock handling method is the single difference. Single difference try to find a master satellite and try to difference across the others. The challenging point of the single difference is the bias of the master satellite may contribute over other satellites. Therefore, it will be a constant bias for all the measurements after the single difference. And the disadvantage of the single difference is it will losing one satellite in the scoring. And the first method we're trying to compare is the single difference with the interconstellation offsets. The master satellite is selected by a scoring scheme, which based on the elevation angle difference on the building boundary, and also the satellite elevation angle, and also measurement CN0 value. And the second method is a particle-based single difference, which we try to find a master satellite on each candidate with the highest score elevation angle, which means that the master satellite may be different across different different candidates' location. And both of the methods is compensate with the interconstellation clock offset, which means all constellation satellites will be considered as a single constellation, and we just have to only select one master satellite to do the single difference. The other receiver clock offset modeling approach is the weighted square, which we're using a standard weighted square with all available satellites, and it consists of the A design matrix and the Q the weighting matrix, and which is a diagonal matrix that depends on the measurement CN0 and the satellite elevation angle. And here's come to the third method, the weighted square with the interconstellation offsets. And this method trying to use all available satellites and calculating the and it will extract the receiver clock bias and for the pseudo-range simulation for all satellites under all candidates. And the challenge point of this approach is that the unhealthy measurements, which is usually the NLOS receiver satellites and also the Multipath satellites, may include inside the receiver clock estimation. Therefore, in this study, we're trying to estimate the clock based on the particle-based approach, which in each candidate will only select the lost satellite to calculate the clock. And here's come to the fourth method, which is a particle-based weighted square with interconstellation. And because it is a particle-based approach, which means that the particle location that we have unknown. Therefore, that we have known the particle location, which means that the remaining unknown is only the clock value. And because it is with the interconstellation offset, therefore, all received clocks should be the same value. And here's only one unknown for the weighted least square estimation. And the fifth method is the particle-based weighted least square, PWS, without the interconstellation clock offsets. Therefore, the clock offset estimation will be estimated separately. And because of the 3DMA GNSS can only handling the NLOS reception, but however, the multipath effect is still an unknown for the positioning. Therefore, we're trying to using the L5 band measurements as the method to mitigate the multipath effects. The benefit of the L5 band mesh signal is it has a higher chipping rates and also a narrower correlation peak. Therefore, it can provide a higher accuracy for the loss signal. For the NLOS signal, it cannot solve the NLOS bias, but it can mitigate the NLOS noise, which means separates the NLOS noise and become less affected the pseudorange measurements. And we are going to using a multipath signal inside the correlator as an example. For the direct path, we can see that the L5 measurements have a sharper correlation peak because it has a higher chipping rates. And if another reflected signal come in for the L1 signal, it's the overlap part actually is becoming a compound signal. And when we try to balance the early and the late channel power, the prompt channel may be shifted from the correlation peak, and therefore it will result in a delay for the pseudorange generation. But for the L5 signal, because it has a higher resolution and the correlation peak is actually separated clearly, especially for the long delay multipath. Therefore, the correlator will only using the sharp and higher power correlation peak to generate the pseudorange measurement, which is more healthy one. And it's seen that more and more smartphones have been support the L5 band measurements. And we think that it is a good chance to make use of the L5 measurements to provide a better accuracy for the positioning in the urban. And in our previous study have been shown that the L5 band measurements have a smaller pseudorange error on the both loss and NLOS satellites. And because the L5 measurement have a smaller chipping rates, therefore we will give a higher weighting for the L5 measurements. And we are trying to use the L1 and the L5 measurement at the same time based on their complementary nature. The first one is the L5 measurement have a better measurement quality. Also, we will keep using the L1 only measurements to maintain a good satellite geometry. Therefore, we will replace the L1 band measurement when the L5 band pseudorange is available. And the replacement will be done on both the CN0 and the pseudorange measurements. Also, we will give a higher weighting for the L5 measurements. And here's come to the system overview. And the input is the 3D building model and also the GNSS data. Then we are distributing the candidates, and in each candidate, we will estimate the satellite visibility, which is the shadow matching, and also we'll estimate this measurement innovation, which is the pseudorange difference. And inside the estimation, first we will simulate the pseudorange, then modeling the receiver clock offsets. And for the NLOS classified satellites, we will try to estimate the reflection delay using the SkyMass 3DMA. After that, we will calculate the measurement innovation. And for the NLOS signal, that doesn't have a reflection point founded by the SkyMass 3DMA, we are trying to remap the NLOS innovation using the likelihood-based ranging. And finally, we can calculate the pseudorange difference to scoring the candidates and integrate the score of the shadow matching. And finally, we can get the position solution based on the weighted average of all candidates based on their scores. Also, and on this part, we set up different experiments using and we're using the smartphone to collect the data in the Hong Kong urban environments. And we are going to use the constellation and frequency on the GPS L1, L5, Galileo E1 and the E5A, GLONASS G1, and also the Beidou B1I. And for the environment selection, we have selected we have 2 experiments on the single-side building, which have a small series multipath effect, and the suburban, which have moderate NLOS reception, and also the multipath effect, and also 2 experiments in the deep urban, which have a series multipath and the NLOS reception. And we will first give the case study on the L1 and L5 band measurements. And we try to estimate the pseudorange error based on the double difference technique, because we assume that all the residual is come from the NLOS reception and the multipath delay. Therefore, the double difference residual should be similar to the pseudorange error at the ground truth. And we are using the ray tracing simulation to label the multipath received satellites as the example. And in the pseudorange plot, we can see that for the L5 band measurements, the pseudorange error is much smaller than the L1 band measurements. And in the PDF plot, we can see that the pseudorange error of the L5 signal is more concentrated and nearly 0 for this multipath satellites. And we're also counting on all pseudorange error for the LOS and NLOS satellites over all experiments. And we can see that 90% of the L5 measurements, the pseudorange error is smaller than 30 meters. And in other words, if we're using the L5 signal for our positioning, it should be really benefits the positioning and improve the positioning accuracy, especially in the urban. And on the later parts, we are going to estimate different receiver clock offset methods. And we are going to estimate based on their positioning mean square error. And we will separate the comparison into 2 parts, which is the single difference and the weighted square. And first, on the single difference of the first 2 methods, we can see that the first method is always outperform the second method, which means that selecting the master satellite using a scoring scheme and using the same master satellite for all candidates will benefit we have a high accuracy on the receiver clock offset in terms of the positioning error. And after that, we're comparing the weighted square. For the third and the fourth methods, we can see that in overall, the fourth method is outperform the third method. And if we're comparing the fourth and the fifth methods, we can see that the interconstellation can really benefit the receiver clock offset modeling. And we can see that the fourth method, the positioning error is always outperform the fifth methods. And in the next part, we are going to select the best method from the single difference and the weighted square respectively for a further comparison using the positioning heat maps. And in this positioning heat map, we can see that the single difference, although it has a smaller uncertainty, but there could be a offset or the bias that contributing by the master satellites. Therefore, the positioning heat map is a bit drift from the truth location, which is the green star here. But for the weighted particle-based weighted square, the high score candidate is still concentrated near the ground truth. which means that the particle-based weighted square may be better to estimate, will have a better performance to estimate the receiver clock offset. And here's the conclusion. The inter-constellation clock offset is important to the ranging-based 3DMA GNSS. And also, the particle-based weighted square is more robust to estimate the receiver clock offsets. And here's the overall positioning results. And we are going to using the frequency on the L1 and L5, which replace the L5 measurements when it's available. And for the receiver clock offset estimation, we're using the method 4, which is the particle-based weighted square with inter-constellation clock offset. And first comparing to the first two experiments, which have a serious multipath effect, the L5 measurements did help the positioning accuracy. And the positioning root square error is within 6 meters. And if we go into the suburban, which have a moderate NLOS reception and the multipath effect, the positioning error is slightly increased to 10 meters, around 10 meters. And after that, we go inside the deep urban, which have a serious NLOS reception and the multipath effect. The root square error is around is within 6 meters. And we can see that even with the smartphone measurements, the positioning error is still performed really good, and which means that the positioning accuracy will be improved even with using a smartphone measurements. And after that, we are going to further look into the integrated solution performance and using the experiment 5 as an example. The experiment 5 actually is located in the road intersection, which means that it doesn't have any clear along or across street direction. And inside for the two ranging-based 3DMA GNSS, we can see that the positioning ellipsoid is actually more likely to be a circle because there's no clear along or across street direction. And after the integration of the ranging-based 3DMA, we can see that the position uncertainty is decreased dramatically. And after integrates of the ranging-based 3DMA and also the shadow matching, the uncertainty is actually slightly increased. This is because inside the integration, we actually given the equal weighting for the ranging-based 3DMA and the shadow matching. And the other point is that we can see that there's two clusters that might have the high score. And if we keep using the weighted average approach to estimate the positioning, it may increase the error of the positioning solution. And here's the conclusion. The integrated 3DMA GNSS can really improve the positioning accuracy. And also the integration factor or the uncertainty should be considered in the future. And the multimodal can affect the accuracy because of the unevenly distributed high score candidates. And here's the conclusion of this study. The L5 measurements can really provide a better pseudorange quality, and the integration of the 3DMA GNSS can improve the accuracy on the across and along street direction. And this study trying to mitigate the NLOS reception and the multipath effect simultaneously. And for the pseudorange simulation, the method 4, which is a particle-based weighted square with inter-constellation compensation, we think is better to estimate the receiver clock offsets. And in the future, the robustness and the reliability of 3DMA GNSS still have to be explored, such as constraint the solution estimation in the time domain. Actually, this is a topic that we are going to present in the upcoming GNSS press conference, and we are trying to using the quickie methods to model the 3DMA GNSS and optimize the performance using a factor graph optimization. And also the uncertainty of different methods should be estimated in the future to have a better integration performance. Also, we find that the initial guess accuracy is important for candidate sampling because the bad initial location may result in the distribution of the candidates cannot cover the ground truth. If we try to enlarge the sampling radius, we increase the computation load. And also, multimodal or weighted averaging may affect the positioning accuracy, especially if the receiver is located near the building. It will drift away from the the distributed candidates that near the building. And finally, that's all for the presentation. And we would like to use this chance to thanks for the reviewers' comments to make this research become better. And if you are interested to our work, you may check out our full paper or visit our website and check out others' work from our group. If you have any question, welcome to ask in the later Q&A section or just contact us after this webinar. Thank you.
Okay, thank you, Ivan. Thank you very much. So Rick, I'm going to moderate myself, okay? Right, so we received 3 questions in the chat rooms. The first one is from Ricardo. He's asking, like, would this GPS positioning work only on the area with Google Map that have 3D mappings, building models? So Ivan, if you don't mind, let me answer this question, all right?
Okay.
Okay,
yeah,
yes,
sure.
so yeah. So this work definitely require that you have 3D building models, but it doesn't necessarily to be the Google's one. Okay, like in our work, we're using the open 3D models, which is level of detail 1 from the Hong Kong government. So we put the Hong Kong government models, yes, we put a Hong Kong government model inside our computer, inside our computing devices, and receiving like U-blocks or like smartphone data, we can do the 3D GNSS. So I understand that after Google announced their 3D then a lots of questions coming from whether we really need to using the Android devices to calculate 3D or not. The answer is negative. So in fact, if you got any GNSS receiver and you could have the 3D building model at your own disposal, then you can do 3D GNSS. So Ricardo, I hope I have answered your questions. So if I don't, so please ask again to elaborate the questions. Thank you, Ricardo. And we have a second question from Sergi. Is the technology the same effective under canopies, not in urban Kenyas? So I would like to share this one, like under the tree canopies, that's a same effectiveness or it's not?
In my opinion, I think if we can really model the tree, it could be have a similar performance. But the problem is the tree, there's different signal nature for the tree, and is possibly for the diffraction rather than only the refraction. And
Yes.
it's unlike for the building material, because building material is usually try to reflect the signal. But for the under the tree, it could be the diffraction signal and moreover than the refraction signal, and is maybe more likely to be a multipath. And but for this point, actually we haven't really studied the how the L5 signal operating inside the tree environment or something.
Yes. So let me supplement on Ivan's answers. So yes, it will be very interesting to test L5 measurements under the canopies, but we haven't done that. But I can share my view of differences under tree canopies and the so-called urban Kenya, the building canopies. So for trees, if you guys can see like this, right? So if we have a satellite here, so we have a building here. If we said this is a tree, terrible drawing, but I hope you guys can understand. So if we put our receiver here, right? So when the signals have a reflection coming in, we can all receive, right? But we said like, okay, if we got a tree, when there is a direct line of sight transmissions, they pass into these trees canopies. So the difficulty for us is that we don't know this is a blockage or a penetration. Okay, we don't know it's a blockage or penetration. It really depending on the density of the foliage that you have. So I have one experience is we do it in Japan, Shinjuku. So when they're in the winter, so there's no foliage, the tree is basically just the sticks. So when we walk around the tree, everything's fine. But in summer, when we walk around the tree, some of the signal are blocked, some of the signal are reflected, diffracted, still be received, and that will cause a very big problem in 3DMA. So I will say how to really like modeling the effect after the tree canopies, the GNSS multipath and diffraction effect after the tree canopies is still a very important research to foster the GNSS urban positioning. Even though I remember in 2005 or 2006, the German teams has published one paper on that, but still we are trying to implement the model they found to 3DMA, but so far the result is not very positive. That's why I can share at this moment, Sergi. But
yeah,
again, yeah, go ahead. Ivan, go ahead.
Yeah, and also the modeling of a tree, I think, is quite important, quite hard inside the 3D model, because the tree is actually more likely to be a dynamic object.
Yeah, because the foliage change along the time.
Yeah.
So it's quite difficult. For example, if you're living in the higher latitude areas, the change of the tree it's really different along the time, isn't it? But if you're living in places like Taiwan or Hong Kong, sometimes it's all green, even it's in winter. So it is really a really complicated an issue that people should think about how to dealing with. Yeah. But I wouldn't say like GNSS is the best way in that scenario. But it's still fun to see how much GNSS can do under those areas, I would say. Yeah. Okay. So Sergio, we have answered your questions. If we don't, again, so please elaborate a bit more or follow up the questions. So the next question is from Thin. Have you mentioned the performance of different 3DMA GNSS techniques in terms of execution times on a mobile phone? Could this technique run in real time on a mobile phone at 1 Hz update rate? So Ivan, I will leave that to you.
For this experiment setup, we don't really executing it in a real-time manner, and we just try to record all the data in the and processing it after we come back to the computer. But in our other research, we are actually trying to have a real-time performance, and if it's written in different platform, it will actually have a different performance. But for our current result, actually is quite encouraged that we can actually using a 1 Hz update rate to perform the 3DMA GNSS. But if for the ray tracing GNSS, honestly, it is quite hard to be real-time implement. But if for the ranging-based the likelihood-based ranging and the shadow matching, it's okay to have a real-time performance in 1 Hz update rates.
Yes.
Yeah.
So
Thank you
again,
for your question.
I would also like to supplement a bit.
Okay.
Like we do have a trying to run the 3DMA, especially the integrate 3DMA GNSS method in a microcomputer, which is NVIDIA NX2, and it is very very positive that it can run in real time. Like we can do it like in half a seconds, even if our coding is totally amateurs, we are just university researchers, but we can do it in half a seconds. So I think that's very positive. And also consider the so-called different 3DMA GNSS technique. I will say like shadow matching is definitely no problem. It's very easy because just basically just comparing the satellite visibility in terms of the calculation of the pseudorange and simulation of the ray tracing stuff. That's nearly nothing there. So it's very easy. And for likelihood, it's also the same. And ray tracing one is very difficult. But one more thing we need to also to discuss under this question is like there's a so-called a particle-based approach, right? So we distribute the particles in a certain area. For this is the initial guess, we distribute around the particle, and we kind of like segment it with a resolution of 2 meters. This is what we do at this moment, 2 meter resolutions. But if your areas become really wide, for example, the radius here, if it's 50 meters, we can still handle. But if it's 100 meters, you gotta understand the calculation is like it's going to increase really fast. So that is the one of the very heavy computation load. when the uncertainty of the initial guess is big. So what we suggest on this direction is that we can actually try to model the likelihood using the Cricket method, so that we become a gradient descent method rather than really a particle approach. And that research will be reported in the ION GNSS Plus in this coming September. So we'll be very happy to share with you on more insight on how do we really reducing the computation loads using this gradient descent approach. So that's my questions. That's my answers for since first questions. Right. So there is another follow-up questions by Singh. Similarly, what's the data size of the 3D building models? Oh, this is an interesting one. So Ivan.
Currently, because we are mainly using the we are actually processing the all the 3D building model and become actually a sky mask here. And for a area about 1 kilometer times 1 kilometers, the process format, the data format is actually around 100 MB.
100 megabyte?
Yeah.
100 megabyte
yeah,
for
megabyte.
1 kilometer.
1 kilometer to 1 kilometers.
Yeah. You can see how we actually like save this data is actually just a raw of data. You can recreate as a vector of 1 to 360, right? So in every column here, we just put in the so-called balloon line over here. We call it the building boundary, right? The building boundary at the second azimuth angle. So we just put in all this number. And I remember using something like a float or shot we're using a float to save the sky mask. But if you are not very particular on the age of the building model, you can actually using a shot to save it. But in response, you will lose some of the accuracy of the building models as well. So it really depends on how accurate you want in your 3D solutions, right? So I hope I have answered your questions as well. So are there any more questions? You can just open up your mic or have a discussion with us. So while we are waiting for more questions, I would like to use this opportunity to shout out to Professor Akio Yasuda, because both me and Ivan we are sponsors to Japanese GNSS summer school in 2000 something years. And Yasuda Sensei is very, very nice, and to provide us the accommodations and also the tickets fly from our countries to Japan to learn the 2 weeks very fruitful of the GNSS class. So I would like to shout out to Professor Akio Yasuda for provide us those guidance. Thank you.
Yeah, thank you.
Right. So we have one more questions from Hugh James. This is difficult to follow. The host is taking over the role as a presenter. James, I'm sorry. Yeah. So yeah. So if you got any follow-up questions, we are happy to answer here. I will let Ivan to speak a bit more. If you guys have any follow-up questions, feel free to contact us by emails. Like we are very happy. We will be very happy to answer your questions. So Rick and Megan.
Yes, thank you both so much. We appreciate your time and effort and the discussion here with answering the questions. Again, the full paper is available for download from our open access journal website at navi, that's navi.ion.org. But thank you for joining us. This presentation has been recorded and will be posted to our website at ion.org later today. And you can view it on demand along with the download of the presentation slides. So again, thank you both, and we hope you enjoy your evening. Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye-bye. Thank you, Asta. Thank you all for your participation. Thank you. Bye.